I will not try to define beauty any more than I would try to define love or fear. You do not define these things. You know them when you feel them. Steven Weinberg, Dreams of the Final Theory, page 131. Weak forces and the standard model. We are rapidly approaching a turning point in this course. We have almost all of the ingredients, the history, the concepts, the terminology to put everything together and talk about the standard model of particle physics, the coherent framework that physicists have today, which we believe explains the bottom layer, the fundamental constituent of the world that we live in. But there is one very important ingredient that's still missing, and that I want to talk about today. It is a weak force, okay? We've been talking an awful lots about the strong force and the quarks that feel the strong force. We talked about the weak force when we introduced the concept of the neutrinos and the beta decays. But the theory of the weak force that we've been talking about so far is an old one that dates all the way back to the 1930s. Enrico Fermi had tried to explain the phenomena of the beta decays, where nucleus spontaneously just transforms itself into different kinds of nucleus, and an electron would go flying out and the neutrino would go flying out, usually undetected. And Mr. Fermi's theory was a mathematical one. You could make predictions about what's the probability of such decay, and there were lots of data. Beta decays are very common in nature. Many radioactive decays involve the weak force as well as the processes in the sun. It's quite a ubiquitous force of nature, even though we don't usually feel it on a daily personal basis. Mr. Fermi's theory was okay, but it was not a particularly deep theory. Although it served to make useful calculations, if you try to push the theory to make really accurate prediction, it began to break down. Wow. For example, Feynman taught us when he studied the electric force of nature that you have to worry about the possibility that the electric field can spontaneously split for a very short amount of time into a particle-antiparticle pair. The vacuum fluctuation. Those virtual matter-antimatter pairs can modify the electric forces between any objects. It's a modification if you are trying to do precision calculations. If you really want to do better than better than 10% or something, you start to have to worry about those sort of fine details, and you can't do that with Mr. Fermi's theory. If you try to look at, for example, how the possibilities for beta decay would change if we take into account the possibility of vacuum fluctuations using his theory, you would get crazy answers. Infinity and nonsense. Yes, infinity means the nonsense. Nonsense for all physicists. It just doesn't make sense, right? Also, Mr. Fermi's theory makes a prediction about weak interactions in particle collisions. Just as in decays, you can also have particles coming together, interacting weakly, transforming and turning into something else. The theory works reasonably well as you go to the higher and higher energies, starting in the 1930s and working your way up through the 1960s at accelerators. The details of the weak interaction depends on the energy. That's not unusual. We've talked about how the strong force of nature actually gets weaker if the particle gets higher and higher energy. That's why the strong force gets easier to predict when you go to higher and higher energies and more modern facilities. The weak force, according to the Fermi's theory, works exactly the other way. As you go to higher energies, the weak force gets stronger. At a certain energy around, it's a little bit hard to be precise because it depends on the process, but around 100 giga-electron volts, the weak force goes off kind of crazy. It starts to go to infinity. Wow. You start to get a calculation that will tell you probabilities are greater than one of some weak interactions occurring. This is a clearly nonsense. that didn't worry anybody for a long time because there were no accelerators anywhere near that energy until the 1970s. Until then, Fermi's theory was working fine, but it was clear to just about everybody that we needed a better theory of weak interaction. It was a shame. We had this lovely quantum theory of electricity. In fact, between 1964 and the early 1970s, quantum chromodynamics, the mathematical theory of a strong force, was developed, and it too became a very well-established experimentally. It was clearly a good theory of nature, so we could explain the strong force, we could explain the electricity and magnetism, but what about the weak force? There were a lot of people who became involved in this business. It is hard to point to just one name. It's not as though there is an Einstein or Fermi who we can say invented the theory. The Nobel Prize went to the three characters: Steven Weinberg's, Abdus Salam, and Sheldon Glashow. I've mentioned Sherry Glashow before. He was the one who proposed the idea of the charm clock, and in some sense, Steven Weinberg was the one who wrote a paper that pretty much put it all together. But each of these three guys made many contributions, and there were many other people as well. There was a young graduate student, T. Hoot in the Netherlands, who wrote a theoretical paper which really established the theory, ultimately as a mathematically rigorous one. He and his advisor, Bertman, received a Nobel Prize at a later time. I think this is a story that occurs more and more frequently in the physics today, and that's it's a little bit harder to point to one genius who come up with the theory all by himself. It may even be true if you go back in history that a lot of people didn't get enough credit for the work they did. Right. What are people looking for? Quantum electrodynamics is a lovely theory that has a quantum mechanics in it. It has a relativity in it, and it has fundamental particles in it. We can do all of those things for any force, so let's try to build a relativistic quantum field theory for a weak force. One of the most important ingredients for both QED and QCD was the idea of gauge symmetry. Wow, gauge symmetry. Okay, it's a very abstract concept. We've talked about it briefly. Gauge symmetry has something to do with the fact that in electricity anyway, it doesn't really matter where you choose to call 0 volts. It's pretty much an arbitrary human convention. No matter what you choose, once you've made your choice, the equations are the same, the laws of the physics are the same, and the experimental results are the same. It's an abstract mathematical symmetry which is a little bit more complicated than that. Gauge symmetry leads us, in fact, to the theory of QED as well as to the theory of QCD. Not only does it help you write down the theory, it makes a clear prediction about the force carrier. Let me remind you about this idea of the force carrier in the field theory. Think about electricity. You have a little charged particle which has an electric field that reaches out into space. That's a classical idea. Now, what is a photon? What is a carrier of electricity? Well, imagine jiggling the little electric charge so the field lines get a little kink, and that kink propagates outwards like the rings of the water when you disturb the water surface. It's a little wave that travels outwards classically. In the quantum mechanics, we think of the propagating wave as a little particle of electromagnetic energy. Yes, a photon. So it's a wiggle in the field that we call the photon. The theory, in particular the gauge symmetry, tells you all about the photon. It says it's without mass. It says it has no electric charge. in the case of the photon, it tells you everything that you could ever want to know about the photon. We see the same thing in the QCD. If you wiggle a cork that's colored, it will propagate a gluon. That's a particle, and the gauge symmetry predicts that the gluon should be without mass. In fact, it's very much like a photon in a lot of ways, except that itself has a color. Right. Michael Faraday originated the idea of the field. I've mentioned Faraday, but I've never mentioned the most important character in the story of the electricity and magnetism. James Clerk Maxwell. Yes. This is a pre-quantum mechanics. James Clerk Maxwell was a Scottish physicist in the 1800s, and if I had to pick the most important physicist far and away between the Isaac Newton in the 1600s and Albert Einstein in the early 1900s, it would definitely be a Maxwell. Maxwell took the idea of the field, a classical field, and turned it into the mathematical field theory for electricity and magnetism. It was a precursor to QED, and in the process he understood the principle of the gauge symmetry. Wow! He wrote down all the mathematical equations discovered that electricity and magnetism are unified. It was a grand intellectual achievement. It's one that even today physicists look back with just amazement that these two forces of nature, electricity. You know, it didn't seem to a physicist in the early 1800s as though they had anything to do with one another. Electricity, as you know, sparks when you comb your hair, and magnetism moves compass needles. But if you hold a compass needle near a spark, it doesn't do anything. There is no obvious connection between the electricity and magnetism. People were finding clues about it in the 1800s, but Maxwell was the one who really unified the two and recognized that in fact, electricity and magnetism are two faces of the one universal underlying force of the nature, which we now call the electromagnetic force. That's what I've been calling it all along. It's like one force of nature, and you look at it from two different perspectives. You see electricity if you are moving this way, and magnetism if you are moving another way. That's kind of the simplistic way of thinking about it. But it really is one fundamental unified force. That unification led to his prediction of the light. Right. That's a classical story. Then the quantum analog of that is in the QED. Again, electricity and magnetism are unified, and the principle of the gauge's invariance now makes a statement about the carrier of the force. So people are now hunting for an analog of this. We would like to do the same thing for the weak force of nature, responsible for these esoteric radioactive decays and neutrino physics. Every mathematician physicist who tried working on this came to the annoying conclusion that if you believe in the gauge symmetry as a principle of nature and try to impose it on the weak force, you should have, by consequence, a carrier of the weak force, which is the without mass. We've talked a little bit about the carrier of the weak force, the little particle that causes the weak force to travel from one place to another, the quantum field of the weak force. We called it the W particle. Nowadays we have the W and the Z particles, and the W particle is massive, supermassive. It weighs almost 100 times as much as proton. It's so massive that it is what makes a weak interaction so weak. It makes it very improbable for a weak interaction to occur, because for it to occur, you have to excite this weak field. That's what W is, the excitation of the weak field, a little traveling wave of weakness. And despite its name, it's very massive. It's very hard to borrow that energy from nature, so the weak interaction has all of its characteristics because the force carrier is so massive. Haha. You have this dilemma. On the one hand, you really believe in the gauge symmetry. It's helped you to understand the other two fundamental forces of natures. On the other hand, if you try to apply it to the weak force, it tells you something that's in direct contradiction with the data. Gauge symmetry says the W boson should be without a mass, but nature says the W boson is very massive. People were, for many years, thought it was hopeless. Even as QED became successful and QCD was already successful, it was rather difficult to understand how to make this all work. The idea that made it work came from a physicist working on something else, as often happens. His name was Peter Higgs. Yes, Peter Higgs. And we'll talk a lot about Mr. Higgs' idea because it's a little bit complicated. We'll devote a whole lecture to the Higgs particles. Mr. Higgs proposed that there was a new particle of nature, one nobody had thought of before. The folks who are trying to understand the weak interaction took Mr. Higgs' idea and said, "Okay, suppose there is a new particle of nature. Let's just do a what if. It's a usual game. What if this new particle is everywhere? It's like a field that's present already in the early universe, and it spreads out throughout the entire universe. It's everywhere. It's inside you. It's out in deep, dark, empty space. The Higgs idea is everywhere. Now imagine that you have a particle that's kind of like a photon. It's a weak force carrier without mass, and it's propagating along through space that's filled with Higgs. The weak force carrier keeps bumping into Higgs all the time, and that makes it slow down and get sluggish. It is as though it acts as if it has a mass because it's trying to walk through this goo of Higgs particles. Alright. It's crazy idea. It's mathematical formal idea, but it could explain how the particle that, for other reasons should be without mass, appear to be massive. People started working out the details. In 1967, Weinberg was able to produce a paper in which he put it all together and had a coherent mathematical framework for the weak force. You could have gauge symmetry and all the beautiful things that gauge symmetry gives you, and you introduce the Higgs particle. This theory reproduces Mr. Fermi's theory at low energies, so that's good. It agrees with all the data so far, but at high energies, no problems. Okay? Everything is finite, everything works, and it makes sense. You can compare with the data, it all works. It's a quantum field theory. You can add many more complicated Feynman diagrams and calculate to as an accurate, high precision as you want. Wow.